All right, hello, welcome back. So the last thing we want to talk about is how can we locate this instantaneous center. In the previous video, we saw how useful instantaneous center is in simplifying the velocity level problems. And we also mentioned that it exists and it is unique, but we don't know where it is. And this is what we will do today. The information that, or the concepts that we will use to locate IC is based on the fact that when you have a body undergoing general motion, the body at this instant appears to be rotating about instantaneous center. So when you have pure rotation, a couple of things happen. Any arbitrary point on the body, a distance r from the instantaneous center, will have a velocity that is perpendicular to the line connecting your point to instantaneous center, and the magnitude of it is r. Is it this way? No, the other way. Yeah, this way. And its magnitude is distance times the angular velocity of the body. So these two information, perpendicularity and the magnitude of velocity, will be very useful in locating IC depending on what kind of information you have. So let's consider a few cases. Case number one, the easiest one, is directions of two velocities of 2 points. Directions of, let's call it VA and VB. So you have an arbitrary body, 2 points on it that let me see, their velocity. Velocity A is in this direction. You don't actually even need to know whether it is to the left or right, but it is along this direction. And point B, another point, let's call it A, let's call it B. It has a velocity along this direction. So let's say this one. Does it work? Actually, no. This is VB, this is VA. Using the notion of perpendicularity, you can say the instantaneous center has to be along this line because it has the velocity has to be perpendicular to this line, and also it has to be perpendicular to the other velocity, so it has to be along this line, and from there, wherever they intersect, you have the instantaneous center. Note that all other points must also have the same perpendicularity constraint. So if you know two directions, you can find the IC and then directions of all other velocities on the body. So that is the easiest. When you have one, let's call it now. Let's call it 1. That is 1. Okay, yeah, 1, whatever. Another condition that things start to be a little tricky is the two directions. Know two directions of VA and VB, but they are parallel. So in fact, you actually have one piece of information that is shared between A and B. And what can you do? So you have a body, VA is this way. Let's make it a bit smaller. You know, VB is this big, but they are parallel. Let me make it a little better. Let's make A to be here for the sake of visuals. So you know IC has to be along this line. You also know IC has to be along this green line. Both of them are perpetually intersecting, so you cannot pick one point. But we said last time that instantaneous center is unique, so you should be able to find it. So you need an additional piece of information. In fact, you had only one, you need a second one. And the second one can come from the magnitudes of the velocities. If your body is rotating with some angular velocity omega, we know that from some arbitrary known position IC, I have distance RA and distance RB to these 2 points. So RA omega is VA, RB same omega equals VB. Or you can divide these together. VA over VB is RA over RB. So the ratios of the velocities equals the ratios of the distances. If you remember geometry, your good old friend geometry, if you construct a triangle, then your RB and RA will satisfy this condition, and that is where your IC is going to be. So you need to know the magnitude of these. If you know magnitude of one, but you don't know the magnitude of the other one, you are in a pickle. That is one case. It is also possible in the figure I drew, both velocities were in the same direction. If you have velocities in the opposite direction, still same situation. You have, let's call this here. IC has to be somewhere along this line, and you can form a triangle. This is where your IC is. That is that. So here, these were two conditions when you knew the directions of velocities and possibly their magnitudes. Another condition that may arise quite frequently actually is when you know something about actual angular velocity. So note that here we didn't need to know angular velocity, but if you know it, that is another piece of information you can use. So you know direction of one of the velocities and the rate of angular velocity. Note that we always have we need two pieces of information. So this is your body. You know VA. You also need to know whether it is to the left or right. So the instantaneous has to be along this line. Where along the line? Some distance r. You can calculate r by dividing V of A by omega. So you can calculate it if you know. You need You need magnitude too, right? Yes, you need direction and magnitude. Yes, let me write it down. Direction, magnitude of VA, and angular velocity. Okay, that is better because you need the magnitude. If you know the magnitude, you can calculate R using the division of VA by omega. And that would be your IC. Is there another way you can calculate or find IC? At this point, I don't remember, and I don't have it on my notes either. But anyways, as long as you know two pieces of information, you should be good to calculate instantaneous center. Sometimes you cannot, but often with many practical problems we deal with, you can find these. Oh, one other thing, let me quickly mention here. Let me bring this down here. We discussed in the last video that if the body is undergoing pure translation, so I'm going to draw a body here, and it is translating this way. It means all bodies undergo same. Let me make this a little bigger. Ah, no, please. All of the points go through the same or move with the same velocity. So in this case, if you want to go with the 1-1 method, your triangle is essentially two sets of parallel lines that meet each other at infinity. So that is where your instantaneous center is. Well, kind of mathematically speaking. And yeah, that is now all I wanted to say. So sadly, there is no similar concept as instantaneous center of zero velocity when you go to acceleration level. So accelerations, you're still stuck with the relative motion equations and all the vector forms. So you have to deal with those. And we'll see a lot of examples in class that how this concept can simplify the problem at a minimum when we are dealing with velocities. So I'll see you then.